measured as efficiency, density, or other attribute. So usually people just plug in a new generation device in their existing design and push the frequency 2-3 times and see how much better it is. And I would consider that's incremental improvement. That's not a proper way of looking at this new generation device. The new generation device has far greater potential than just plug-in and replacement. Now, how do you realize the potential? In order to do that, you really have to start from scratch. Throw away everything you do, all your old practice, start something new. And that basically is my story. Now let me then show you in terms of switching loss performance. The red curve is a silicon device. Turn on energy loss is this curve. Turn off energy loss is this curve. And the blue curve shows the GaN device. Turn on energy, turn off energy. Turn on energy, about half of the silicon device. Turn off energy is almost zero. Almost zero. That's unusual. You never see a device that had this almost negligible turn off loss, but that's what GaN is. And then you compare silicon carbide with the IGBT device, and you can see similar performance. The red curve is turn on energy, turn off energy. Then the blue curve is turn on energy, turn off energy. In this case, the turn on energy of silicon carbide is about 1/3 of the silicon device, which means less loss. And turn off energy is small in comparison with the silicon device, significantly small, which also means silicon carbide also have a potential to run at a higher frequency. Today's current practice today is take a current design, switch to silicon carbide, increase the frequency 2 to 3 times. And they are happy with the result of it. What I consider is incremental improvement, but most people would have it. This is a good device, they're going to do it this way. Again, that's not the proper way you treat this new generation device. So my story then started with a simple comparison. Let's see if I have a simple buck converter and I designed for 1.2 kilowatts, but I'm going to run at 1 megahertz. So is it possible to run GaN in 1 megahertz? The conduction loss for the two switches are small, but the turn on loss is tremendous, huge. So it is not possible to run the GaN device at the megahertz, as I said, 10 times faster than the silicon device, because there's tremendous large turn on energy loss. But turn off energy loss is negligible. You never see a device that has such a contrast. High turn on loss, negligible turn off loss. So if we use one of the concepts we developed earlier, zero voltage switching. Now if I do zero voltage switching and run the same frequency, then I wipe out the turn on energy loss. No turn on loss, no turn off loss, no gate drive loss. I have never seen in my life that I now run into a device I can truly eliminate switching related loss by increasing frequency 10 times. That has never happened in the past. You can see I can apply soft switching technique for silicon device and run the megahertz. Yes, you can do that. Your turn on loss is small, also small, but your turn off loss is not small. Your gate drive loss is not small. So by running at a megahertz for silicon device, even with soft switching, is not worthwhile. So most people still using MOSFET device, soft switching, running a couple hundred kilohertz. That's how they do. And likewise, in silicon carbide device, if I build the same circuit, let's say for a little higher power, 4 kilowatt, I'm running at 20 kilohertz, which is usually people would run at this power level, at this frequency, at this power level. So you can see turn on energy, conduction loss is large, turn on loss is large, and turn off loss is small. Drive loss is small, so the total loss is high, and significant part of it is switching related loss. But if you do soft switching, run at the same frequency, conduction loss slightly increase, turn on loss is almost negligible. Turn off loss is insignificant. The total loss is significantly reduced. Okay, so now if you do exactly this, then you actually see a benefit of having a higher efficiency performance. But if you try to operate this at 15 times higher switching frequency, and what you see is your small increase in conduction loss, you still have no turn-on energy loss, you start to see somewhat turn-off energy loss, and then the total loss is still smaller than 20 kilohertz hard switching. So which one would you like? Soft switching or hard switching at a 15 times higher frequency? At 15 times higher frequency means this equipment is dramatically reduced and potentially cost would be dramatically reduced. So that is a significant benefit. Most people have not yet realized that is the potential of silicon carbide device by increasing the switching frequency 15 times using soft switching, some kind of soft switching concept. Okay, so that is a new generation device. Okay, the question is, now you have this new generation device that you can have much higher switching frequency and negligible switching loss. What would you do? What would you do? Are you going to do the same practice, same design, and just plug in a replacement device and be happy with it? Or you should start from scratch, from the beginning, see, and challenge your design practice, okay? So that is my message now, and I will show you example. Most people are, when they are start playing with the wide bandgap device, they have trouble. And we did have trouble for the first 2 years. We're struggling to how to make it work. And most of the practical engineers, when they run into trouble like this, they just give up. They don't have time, resources to overcome this difficulty. So what are the difficulties? Let me illustrate it in here. Now, this device is recommended to operate in the gate voltage is 4 to 5 volt to minimize the RDS. But at 6 volt, this device reaches breakdown voltage. Okay, you have very little margin. So you would like to bias the gate at a 5 volt, but slightly over that you break down the device. That's what initially we run into that problem. It's very easily to destroy the device, and you have to be very careful. But today's devices are more rugged. So you can momentarily exceed 6 volt as long as there's not much energy, very short time, device would survive, and that give you a somewhat higher margin to design. So I give you an example. My first graduate student worked on this. He's a very good designer because a lot of design experience. So he's just apply every knowledge he had and using it again. He for the 1 year a time, he burned off all the sample I was able to get it. I said, what lesson have you learned? I don't know. I do not know how fail. So, but he burned all the devices. So, and I find out this student is not suitable for working on this area because he's got so many bags behind him, his past experience in design. None of them work. So I assigned 2 brand new students, had no experience in design, said, you two start this. And they started and spent another year and figure out how to make it work. And from that point on, then we were able to demonstrate what are the potential for this generation device. It is important for me to point this issue for you because this is very discouraging for any engineer who start working in the field. Start using GaN device, they all run into this problem. Most people then just give up. Or says, I'm not going to run 10 times higher switching frequency, I'm going to run same frequency or 2 times, 3 times higher the switching frequency. And when they do that, they do not see a much value added justification for them to change. And that's what the story is today. Two things. So threshold voltage is low, very easy to turn on, means small noise will trigger it on falsely turn on. And breakdown voltage is low means very easy to break down device. And another aspect is DVDT, DIDT is high with respect to silicon. Then you can see the silicon device. Whoop. You can see the silicon device. The DVDT and DIDT are here, and the silicon carbide device, the GaN device are roughly 5 times, even 10 times higher in DVDT and DIDT. And these two issues are very difficult to deal with. And again, you have to design very carefully. You have to lay out circuit very carefully. You have to control your parasitics very carefully. Okay? Require a lot of effort. And as of today, all the commercial available device for high side driver for silicon device, and none of them work for you. You just have to redo it. These are all the commercial available high side driver for silicon, none of them would work for this. And so these are the difficulty people initially run into. Okay, now with that, now I'm asking a serious question. Given the device without switching loss, what would you do? Okay? Then the next question is, figure of merit is usually used as a measure of how much improvement of new generation devices does it make sense. You see, device manufacturer talk about figure merit. Application engineer talk about figure merit, and now I challenge it. Does a figure of merit make any sense in this new generation device? I said, it doesn't make a lot of sense to me. What is figure of merit means? Figure of merit is used to identify device with a balanced conduction loss and switching loss. So a device that has a conduction loss and has switching loss, figure of merit is RDS times Q. RDS is for conduction, Q is for switching. So the product of the two is give you the idea of the total loss of the device is figure of merit is small. Figure of merit is small means the device is better. But now with this new generation device has no switching loss. If you do some switching, so do you still want to use figure of merit? I do not think it makes a lot of sense. Conduction is the only thing. I'm worried about switching is not a consideration anymore. And just to give you an example, some of my friends always kid me and says, well, Fred, you invented the soft switching concept, everyone using it today, but with this new generation device, it's so fast, there's very little switching loss, and now we can now run happily with hard switching. And that is completely wrong concept. It is, if you run a hard switching, you can push the frequency 2-3 times, that's all you can do. If you want to push frequency 10 times, there's no chance to do with hard switching. So all the potential benefit you will not be able to realize. So that's how wrong people's perception can be. And unfortunately, the majority of people think that way. Okay, so the message is, we really should re-assess our design approach and our trade-off practice. We have to redo this whole thing because this new generation device is so different from what we know. So here is an example of how a data center power supply is built today. And you have a two-stage filter. Okay, that occupies about a quarter of the space in the board. Then you have a bridgeless PFC, the most efficient PFC circuit that occupy about a quarter of size of the board. Then you have a DC-DC converter that occupy about 50% of the board. And this is our best topology people consider is for this application. And they usually run is about 100 kilohertz with a 96% efficiency. and up to 30, 50 watt per cubic inch power density. This is the benchmark. This is best of the practice today. Now, the DC-DC converter design usually using resonant converter because we have low voltage output, high current output, synchronous rectifier. We have parallel synchronous rectifier. We have the parallel secondary winding in order to reduce winding loss, in order to reduce conduction loss for synchronous rectifier. By this practice, when you start a parallel more than 2 devices, it's hard. Now, in cases like this, you probably have to parallel a device to get the efficiency you want. And then a device, there are 2 issues. Current sharing is a problem. You connect all the A devices in one dot, one point. That termination loss is not insignificant. These are problems. So, and transformer design is very complicated. And there were attempts in the past to redesign the transformer using PCB, essentially eliminating termination-related loss, and that has a better efficiency, but this design is very hard to manufacture. So, and when this shows up in the market for a while, then it withdraw from the market because it's expensive to build a system like this. Now, this is the state of the art of design for this circuit. Now, let's see what can GaN device do. So, if we start with this silicon device topology, and we push frequency up 10 times, okay? Then I can, instead of using one transformer for this design, then we begin to break one transformer down into 8 transformer. Why 8 transformer? Because I need 8 SR in the secondary. Instead of parallel SR, I would rather than parallel transformer. Okay? Now, parallel transformer for silicon device, it is impossible. It would become so large in physical size. But now I'm pushing frequency 10 times, so physical size reduced to 1/10 of it. Now I can afford to parallel A devices. But parallel A device, still the size is relatively large. Then we begin to integrate this individual device. Now let me say, first of all, why should I want to use A device? 2 reasons. One is I do no longer need a parallel SR. The second reason is that I want to use different way of design transformer. I want all the transformer winding to be on the PCB. And the PCB should be no more than 4-layer PCB. That's commonly used PCB in all design practice. So per transformer, there's only 2 turns in the primary side, 1 turn in the secondary side. So easy a design. And while in the previous case, I showed you a transformer is very complicated. There are literally hundreds of turns in there. How could you possibly build that in PCB? There's no chance to do. Now, with this then, we now divide the complicated problem into simple problem and conquer simple problem with a simple solution. So what we have now, I showed that last time, yesterday, in the illustration. Let's talk about 2 transformer. Now, how do we integrate 2 transformer into PCB? 4th-layer PCB, primary number of turns is only 2 to 1 to 1. So 2 transformers just 4 turns, okay? So now you have, this would be, per transformer, there would be 2 turns in the primary side, 1 turn in the secondary side. So you put 1 turns in the 1 layer, 1 turns, primary side current, and in this case it's counterclockwise, and in the other case is clockwise, just opposite direction. What purpose? Why do I want to do that? Because when I do that, the flux would be in opposite direction. When I turn the 2 core 90 degrees, then the center leg of the flux canceled. So you don't need a center leg anymore. You eliminate two legs in the center. Now you have the two UI core become one UI core. That represents two transformers. So you cannot find a transformer simpler than this, but it's in a 4-layer PCB. So you have a 4-layer PCB, primary, secondary side, primary side, primary side, secondary side, 2 to 1 to 1. Okay, so you can continue this exercise. Now with 8 transformer, what do we have? We're just using 4 UI core. You put all the 4 core in a row, and that is your transformer design. Now that is a simple design. If you remember the state-of-the-art hardware practice, the converter, DC-DC converter, pretty complicated. Now it will be the new DC-DC converter. It's rather simple. Everything is done in PCB on the 4-layer board. So we talked about that yesterday. In terms of efficiency, this efficiency is even better than the conventional practice. Roughly, we're getting about 97.5%. Okay? So that's DC-DC. And one more thing we do, very important aspect. If you can afford 2 more layers, make a 6-layer transformer, because this footprint is so small. 6-layer board is still very economical. What you can do is putting 2 shield layers between the primary and the secondary. And when you put 2 shield layers between the primary and secondary, you completely block the common mode noise that going through the transformer is being terminated, blocked. Okay, so you have a common mode noise reduction of 23 dB from 150 kilohertz all the way up to 30 megahertz. Nobody has ever been able to do that before. This concept of shielding doesn't apply to traditional design, only to the PCB design. Okay, so and this is achieved. I showed that also yesterday. Now, the next question is, I also talked about yesterday briefly, PFC. Now, can we integrate magnetic in the PFC? Nobody has ever attempted to integrate magnetic inductors in the PCB. Why? Because number of turns are too high. Integrating inductor in the PCB is not like integrating transformer in the PCB. In the transformer, you have interleave primary, secondary, and you can cancel the magnetic force, MMF. But interleaving inductor is everything is in the same layer. There's no cancellation of field and loss is high. So you can see, obviously, if you use 2 PCB inductor, even I'm running this is running this at 1 to 3 megahertz. 1 to 3 megahertz, variable frequency, critical mode operation, achieving the soft switching. So at this frequency range, I don't need too many turns. So I can easily do this with 6-layer transformer, 6-layer PCB. But the loss in the winding are 4 or 5 times higher than the conventional practice. So who would want to do something like this? Not worth it. So people usually don't do that. The next thing we do is we put 2 inductor, well, we have 2-phase interleave, so we have ripple cancellation. This is the idea of reducing differential mode noise. Now, if we do a negative coupling concept, this is the concept we invented in the Virginia Tech, and we can reduce the core size. But in addition to that, we can actually have a benefit of borrow. This will be inductor 1, this will be inductor 2 in red. I can borrow a term from inductor 2, put that in the middle of inductor 1, and likewise, inductor 1 turns in the middle of inductor 2. And this with the opposite current, and this give you the interleaving effect. This effect would dramatically reduce the winding loss. Okay, now the winding loss is just somewhat higher than the conventional practice, but much lower than the left-hand side. So, and this will make the total loss about the same. Okay, now we have a design with an integrated inductor that has about the same loss as a discrete inductor with this wire. Okay, but that's not the end of it. Another concept we developed at Virginia Tech is we can use the balance concept to improve common mode noise for topology like non-transformer type of topology like PFC circuit. Now the concept is simple, the Western bridge concept. In Western bridge, we all know that